Okay, we'll get started today, so get settled in if you're walking in just now. All right, so we're going to move on to the next part of Chapter 4. Again, this will not be on the first exam. We're going to talk about today molecular polarity, which is very much related to the things we talked about last time with the three-dimensional structures of molecules. So to kind of review what we did last time, here's sort of a summary table of all of it. So we went over all these different possibilities for electron group arrangements where you have different numbers of outer atoms and lone pairs on the central atom, and that's going to then dictate the geometry. And so each steric number is going to have an electron group arrangement associated with it, which would be this first column here, and that's also then going to be the molecular geometry when you have no lone pairs. And then as we start adding lone pairs, we get different molecular shapes that result as, by virtue of having those lone pairs occupying one of the positions. So I guess I'll just, to finish this off, give you an example of each of these to show that these are all real molecules. And then you'll see that, and then we can work through some more later on. So an example of AX2 would be CO2. AXE would be CO. And so what I encourage you to do is go, if you want to, draw Lewis structures of all these that I'm going to give you and convince yourselves that they do in fact match the AXE notation that they're all applied to. So this would be something like BH3, AX2E, what would that be? I guess SO2 would be an AX2E. AX4 is very common, especially for molecules that contain carbon, so something like CH4 would be AX4. AX3E is another common one. We saw that last time with NH3 and also PCl3. AX2E2, perhaps the best known example of this, is H2O. And then as we get into the steric numbers of 5 and 6, remember that in this case you're going to definitely automatically be expanding the octet, because now we have at least 10 electrons around the central atom, or at least 12 electrons around the central atom. So you're only going to see these for central atoms that are in the third row of the periodic table or below, those that are able to expand the octet. So for AX5, you could have something like PCl5. AX4E is not a terribly common one, Seesaw, but there are some examples of it like SF4. And then AX3E2, which would be T-shaped, would be something like IF3. So there are some compounds where a halogen is also the center atom, particularly when it's iodine, something like that. AX6, the best known example of this is SF6. AX5E, man, we have a time coming up with an example of this off the top of my head. I guess you could have IF5 as well, would be AX5E. And then finally, AX4E2 would be something like xenon tetrafluoride. So there are some examples of molecules that have noble gases at the center too, especially xenon. So these are kind of rare, but they are out there. And I think I forgot one on here. AX2E3 is one of the linear ones. We saw that in the notes last time, and this would be an example. This would be xenon difluoride, XEF2. So again, not a particularly common one. These two here, but they do exist for noble gases, especially. All right, so those are just real examples of all of these. So that's why we went through every single one, because there are real molecules that have those shapes. To see how well you understand this, we're going to start with a bonus quiz. So if you have your clickers, please get them out. And again, I'll have a timer that starts, so get your clickers out as quickly as possible. But I won't really start timing this until I actually bring it up. So I'll start. See if I can do this without messing it up. Okay, so then I think you'll have somewhere around 2 or 3 minutes to do this one. It's a typical VSCPR problem where we're going to ask you to identify the number of electron groups and the molecular geometry. So I'll go ahead and pull this up. And for those of you, if you need this, there's the session ID there. I'm finally starting to adapt and learn how to use this program properly. All right, and then as soon as I press the button again, you'll be able to start entering. Well, you can enter answers anytime, but now the timer will start. So there we go. 3 minutes. Should be plenty of time. So this one will count in case it wasn't obvious. Two minutes. Start the video. So 59% of you had C, which is 5 electron group seesaw, and I like that answer. So if you had that, you were correct. I'll save this. Okay, so let's get back and refocus. I'll go through this problem quickly. So those of you that had C were correct. Let's see why that is. Okay, so the first thing we have to do is draw the Lewis structure. So anytime we're asking you about the electron group arrangement or the molecular shape, anything related to VSEPR, it starts with the Lewis structure. So we have to count electrons first. Let's go to the periodic table quickly. All right, so tellurium, Te, is down here in group 6, so it's going to have 6 valence electrons. This is sort of on the border between metals and nonmetals, so it can certainly have behavior from both, but it is in the group 6, so it's always going to have 6 valence electrons. And then chlorine, we've seen that a lot, is in group 7, it has 7. So we have 1 tellurium and 4 chlorines we have to count the valence electrons for. So we have 6 from there. And then from the chlorines, we have 4 and we have 7 each, another 28 electrons. All right, so we're going to have 34 total valence electrons around our central atom. And then we just start with single bonds. We complete the octets by adding lone pairs, first to the outer atoms, of course. All right, at this stage, we take stock of where we are. 4 chlorines with 8 electrons each is 32 of our 34 electrons, so we still have 2 more left. Those have to go on the central atom. And as I talked about last time, for VSEPR, if that's really the end goal, we don't need to worry about drawing double bonds and things like that. So in this case, there won't be any double bonds. We almost never see that when we have halogens on the outside, as the outer atoms. But still, even if there were double bonds, we don't necessarily have to do that. We can start answering the questions now. So for the number of electron groups, remember that each atom that's bonded to the central atom and each non-bonding pair of electrons counts as an electron group. So we have 4 atoms and 1 lone pair, so we have a total of 5 electron groups. And in this case, they're categorized as AX4E because there's 4 atoms and 1 lone pair. And so that's going to be the first part of our answer. And then the second part, we have to see which geometry that corresponds to. So, one way to approach this is just to memorize the table at the beginning of this notes. That's a little bit laborious, so it's always helpful to understand where this comes from. So if we have 5 electron groups, it's going to give us a trigonal bipyramidal arrangement of those electron groups. That's the starting point anytime you have 5 total electron groups. The lone pairs always go on the equator, the triangular part of the molecule, and then we just have our chlorines and the rest. And this is one of those geometries, again, it's not the most obvious to look at, but it's called seesaw. All All right, so there are 5 electron groups, and it's a seesaw geometry, so C was the correct answer. So A had the correct number of electron groups, but remember we're only going to see a tetrahedral geometry when there's 4 electron groups. So whenever you have 5, you're never going to see tetrahedral, and the rest of these had 4 electron groups as part of the choice, so that's not going to be correct either. All right, so take some time to practice that on this week's homework, and it's going to be very important for what we talk about today. So what we're going to talk about today are the polarity of molecules. So we did introduce bond polarity in Chapter 3, and that is a topic that could be on the first exam. So just a quick review of that. So remember, what polarity refers to is the idea that when we have 2 covalently bonded atoms, they're not necessarily going to be sharing the electrons exactly equally. So if you have different electronegativities for the 2 atoms, then there's going to be more electron density towards one side of the bond than the other, towards the more electronegative atom. So the direction of the polarity is always towards the more electronegative atom, and that means that there's more electron density near the more electronegative atom. So each individual bond in a molecule is going to have some polarity associated with it, unless the 2 atoms are the same or the 2 electronegativities happen to be exactly the same. And so for any simple bond, you're going to have some polarity. And the example that I gave you in class was HF, where fluorine is the most electronegative atom on the periodic table. So no matter what it's bonded to, except for itself, there's going to have to be a polarity pointing towards fluorine. The way that we designate that is either with an arrow pointing towards fluorine, so it's a dipole where the negative end of the dipole is towards the more electronegative atom, or perhaps a more convenient way to think about it is you have a delta plus and a delta minus, meaning you have a partial positive charge on hydrogen, so you have less electron density over here. You have a partial negative on fluorine, meaning there's more electron density on that side of the bond. And even though the overall species and the overall bond is uncharged, there's an imbalance of that charge in the bond. So the magnitude of the polarity depends on the difference in electronegativity between the 2 atoms. And this is another topic that should be a review and will come up on the first exam, is how do we determine which bond is more polar or less polar? And that's by looking at the individual electronegativities of the 2 atoms, and the difference between those is going to relate then to the magnitude of the polarity. So let's say we have carbon bonded to all of the halogens as an example. So we have the carbon-fluorine bond is certainly going to be polar, and it's going to be polarized towards fluorine. And so most of the halogens are more electronegative than carbon. And so if you have carbon bonded to chlorine, we still have a partial positive and a partial negative charge, but since fluorine is more electronegative than chlorine, it's going to have more of a pole, it's going to have more of the electron density pulled towards it. So this is going to be a more polar bond. They have one atom in common. This one has a more electronegative halogen on it, so it's going to have more negative charge on the fluorine. So this is going to be the most polar, and followed by this one. And then by the same token, then carbon-bromine is going to be slightly polar, but less so, because bromine is less electronegative than chlorine, so there's going to be less negative charge now. And then finally, if we go to the last one, which is carbon-iodine, these 2, by coincidence, have pretty much the same electronegativity, so this is roughly nonpolar. Okay, so the carbon-iodine bond is nonpolar because these 2 electronegativities are almost the same, and then all of these are polar, but the polarity increases as you increase the electronegativity of the bonding partner. So we will be asked in some cases on the exam to compare polarities, and that comes down to the difference in electronegativity. But what we're interested in talking about today is molecular polarity, which is the polarity of an entire molecule. So we've moved on past just simple bonds that involve 2 atoms. Now we're starting to draw Lewis structures and determine 3-dimensional shapes for molecules that have many atoms in them, and that they often have 2-dimensional or even 3-dimensional shapes associated with them. So we want to know if the entire molecule itself is polar. That is there an uneven distribution of charge over the whole molecule or a large portion of it? So that's going to be our basic definition here. So molecular polarity still refers to an uneven distribution of charge. And it's going to be an uneven distribution over the entire molecule or a large portion of it. And so what we mean by that is if you've taken introductory biology classes and you guys talked about certain biomolecules, there are some larger molecules that are going to have parts of the molecule that are polar, parts of the molecule that are nonpolar. If you have something like a fatty acid you may have heard of. But at any rate, for our purposes, we're going to be mostly talking about relatively simple molecules where polarity is going to be defined as an imbalance of charge over that whole molecule. And so again, that means that some side of the molecule is going to have a slight negative charge and the other side is going to have then a slight positive charge. This only applies to neutral molecules, neutral covalent molecules, so the whole thing is still uncharged, but in some cases, depending on the geometry and the electronegativities of the atoms, you're going to have an imbalance of that charge. So there is a unit for polarity. We're not going to really talk about the quantitative aspect of this, but you can measure the polarity of molecules if you wanted to. The unit is called the debye, named after somebody, and I don't think you'll see any homework problems on this, but just to be familiar with it. This unit is derived from simpler units. So it's for a single molecule, it's going to be very small, of course, in terms of conventional units. So it's coulombs times meters, but a 1 debye is about 10 to the minus 30 coulombs times meters. So it's basically an electric field measurement. You have a charge and a distance that electric field applies to. So this is your coulombs, which is the unit of charge, and then that's meters, which is the unit of distance. And then we have an abbreviation for dipole moment. So what you're measuring when you measure the molecular polarity is called the dipole moment. So another way of saying a molecule is polar is you say the molecule has a dipole moment, and then there are ways to quantify that, and that's abbreviated with a Greek letter that we should be familiar with, mu. So we use that same Greek letter for 10 to the minus 6 and to abbreviate dipole moment. There's only so many Greek letters we can use in chemistry. We have to double up sometimes. All right, so that's some information about molecular polarity, but again, we're not going to deal with the quantitative aspect of it. But what we are going to deal with is predicting molecular polarity, looking at a compound and saying, is this polar or is it not? And that's going to be the primary goal of what we have to do on homework and exam problems related to this. So there are some criteria that we need to keep in mind when predicting whether a molecule is polar or not. And the first one is that it has to have polar bonds. You cannot have a polar molecule if all of the individual bonds themselves are nonpolar. Now, in most cases, you will have polar bonds, but there are some examples where you can automatically eliminate them and know that the bonds themselves are not going to be polar. So if we have what are called homoatomic molecules, and that means you have molecules that have all of the same atom involved, then those definitely are going to be nonpolar. So a lot of elements occur as diatomic or even higher. We'll talk about this more later on. But if you have molecules where every single atom is the same, you can't have any polarity because there is no polar bonds to be had in that molecule. There is one exception to this, but we're not going to get into it. That's ozone, O3, where the shape of the molecule does give it some polarity. But at any rate, we're going to mostly just talk about the simpler cases. And if you have a homoatomic molecule, N2, P4, S8, I guess there's probably others you can dream up, then you can just look at the formula and know that it's nonpolar because there can't be any polar bonds in this. But for every other molecule where you have two or more different atoms involved, you can't just look at the formula and tell whether it's polar or not. You can't just say, well, it has to be polar because it has polar bonds. The other part of this is the geometry, and so that's why we're talking about this now after we've introduced VSEPR. So in order to have polarity, the molecule must have polar bonds, but you also have to consider the geometry as well. So just having polar bonds is not enough to necessarily make it a polar molecule. So the presence of polar bonds does not guarantee that a molecule will be polar. All right, so it's only by looking at the three-dimensional shape of that molecule can we really predict whether it's going to be polar or not. You have to have that consideration as well. So we're going to go through then today a bunch of examples of this and how we want to think about this when looking at real molecules. So first let's start with a bunch of examples of molecules that have polar bonds but are themselves nonpolar overall. All right, so what happens in this situation is that each individual bond has a dipole associated with it. So there are individual dipoles on the bonds. All right, so it's not that what we learned in Chapter 3 is invalid here. The bonds themselves are polar, but these individual dipoles cancel out to give a molecule that is nonpolar. Okay. All right. So some classic examples of this. One, we've mentioned this one in a lot of contexts. CO2. So CO2 is completely nonpolar, and it has carbon-oxygen bonds. And as we know, oxygen is more electronegative than carbon. So oxygen is the second most electronegative atom on the periodic table. So each of these carbon-oxygen bonds is going to be polarized. But carbon dioxide has a linear geometry, and so what you have a dipole going this way, left to right as I've drawn it. You have another dipole going right to left, and they completely cancel each other out. So in that, there's no dipole for this molecule. All right? Or if you want to write it in terms of delta plus and delta minus, this oxygen is delta minus, this oxygen is delta minus. The carbon would then be, I guess, 2 delta plus because there's 2 polar bonds pulling in either direction. But in that, there's no net polarity in this molecule. Now, one way to think about this, which is pretty straightforward for a linear molecule like this, is imagine that each of these dipoles are vectors, and imagine that you're pulling on the molecule in each of those directions. So we're gonna pull on this bond here towards me, and then someone else on the other side is going to pull in exactly the equal and opposite direction. Those 2 poles cancel out, and you don't have no net translation of the molecule. Then it's going to be nonpolar. So you can kind of think about it in a physical sense. It's not really what's going on at a molecular level, but if you want to think about it that way, imagine that you're playing tug of war with these 2 bonds. You have 2 bonds of equal polarity in opposite directions. If you're pulling on each of those, you're not going to have any translation of the molecule. The molecule is going to stay put, and that means that overall it's nonpolar. Now, some of the other geometries are a little bit less obvious. So this is a nice, one-dimensional linear molecule where your dipoles go in completely opposite directions, but in some cases it's not as clear to look at. So if we have BF3, this is going to be one of our AX3 trigonal planar molecules. In this case, you have bond dipoles going towards each fluorine, and they will also cancel out and make a nonpolar molecule. So to fully understand this, you'd have to divide each of these vectors into x and y components. So if you're good at trigonometry and you've done those sorts of things before, you could probably convince yourselves that this is true. But whether you want to go through that math or not, and I'm not going to, when you have 3 dipoles pulling in an equilateral triangle, they're going to totally cancel out. So this one pulls straight up. You have the down components of these ones that cancel that out, and then these ones pull equal and opposite in what we'd call the x direction in this orientation. So when you have a trigonal planar molecule, you have all the individual bond dipoles cancel out. And then even for more complicated ones, 3 dimensions now, if we have a tetrahedral molecule, carbon tetrafluoride, again, each of these is going to be a polar bond, but all of those polarities cancel out. And if we had, a giant tetrahedral model up here, and we had 4 people pulling equally on those 4 bonds, the molecule wouldn't move. And that you could convince yourself then that there is no net polarity in this molecule. So these are 3 examples where you have polar bonds and you have nonpolar molecules. But then, of course, there are many examples where the molecule has polar bonds and is also polar, and this is primarily going to be the case when you have lone pairs. So we'll come back to that idea in a bit, but we notice that all 3 of those examples up there didn't have any lone pairs on the central atom. But in a lot of cases, when you have lone pairs, you're going to also have polarity. So this is going to be the case when the molecule is not perfectly symmetric and the 2 dipoles or the 2 or more dipoles don't perfectly cancel out. All right, so if we think about a pretty simple example now with water, we know that water has a bent geometry, has the two lone pairs occupying the other positions of the tetrahedron. And each of these OH bonds is going to be polar. Oxygen is more electronegative than hydrogen, so you're going to have a bond dipole that points in from each hydrogen to the oxygen. All right? And so in this case, the two dipoles don't cancel each other out. They're pointing in roughly the same direction, or at least they're going to reinforce each other in the y direction. So if we add these two individual dipoles together, they reinforce each other. They're not equal and opposite in this case, as they are in a linear molecule. And what you get then for the molecular polarity in water is an overall dipole moment that points straight up. And so what this then tells you is that this region of the molecule near the oxygen has more negative charge, and then the bottom part of the molecule, as I've drawn it near the hydrogens, has a partial positive charge. Again, not full negative and full positive charges, but some imbalance of the charges there. So in this case, you have an example where, because this isn't a linear molecule, the two dipoles don't perfectly cancel each other out, and they reinforce to give you a net dipole in this direction. So this really is just vector addition. If you've covered that in any of your physics or math courses, this may be a little bit more intuitive to you, but the net result is that, however you want to think about it, these two dipoles add to each other, and you get a net dipole from bottom to top as I've drawn it here. And then finally, there are some examples where, as I said, the polarity is largely determined by the shape of the molecule, but it is possible to have a case where two molecules have the same basic shape, the same AXE notation, but different polarities. And so, to give you some examples of this, molecules without lone pairs can be polar, but really for this to happen, they have to have more than one type of outer atom. All right, so we saw 2 slides ago that if you have a molecule without any lone pairs, we saw linear, trigonal, planar, tetrahedral, and there's no lone pairs on the central atom, all the outer atoms are the same, all of those dipoles cancel each other out, and you have no polarity. But if you have 2 different atoms bonded to the central atoms, each of those bonds is going to have a dipole, but they're not going to be exactly the same. So the one that I gave you 2 slides ago was carbon tetrafluoride. And this one's nonpolar because each of the individual bond dipoles cancels. But let's say we replace one of these fluorines with something else. I'll just pick hydrogen as an example and make this compound here, which would be called fluoroform. Not that we're expecting you to name these ones, but let's say we replace one fluorine with an oxygen. This is still a tetrahedral molecule. It's still AX4, but in this case, something a little bit different happens. So we still have the same bond dipoles for the carbon-fluorine bonds, fluorine more electronegative. But then if we look at the carbon-hydrogen bond, carbon is actually a little bit more electronegative than hydrogen. Hydrogen is not in a very good spot on the periodic table to easily predict that, but carbon and hydrogen are similar in electronegativity. Carbon is a little bit more electronegative, and so we get a small dipole that points in this direction towards carbon. And so now the dipoles no longer perfectly cancel out because you have these 3 that sort of have a net pole going down. This one reinforces that a little bit, and so this is going to have some net polarity. All right, so it's still a tetrahedral AX4 molecule, but now the dipoles don't cancel out, and there's a net dipole in this case. And then finally, if we have, let's do this one here. I want to make sure I don't do the same one that's in a later example. Okay, so let's do CCl2F2. Another tetrahedral molecule where now it's 2 fluorines and 2 chlorines. All right, so in this case, I'm going to try to draw this to scale to some extent. All of these bonds are polar, and all of these outer atoms are more electronegative than carbon. So you're going to have a polarity for each bond that points towards the outer atom. Now fluorine is very electronegative, so you're going to have a large dipole for each of those bonds. Carbon-chlorine bonds, as we saw when I was introducing this and reviewing bond polarity, this is less polar than carbon-fluorine because chlorine has a smaller electronegativity. So you're going to have bond dipoles, but they're going to be smaller, so I'll draw those with smaller arrows. Alright, and so again, in this case, they don't perfectly cancel each other out because you have a stronger pull towards the fluorines than you do towards the chlorines, and so you're not going to have all of those cancel out. And this is going to be a little bit hard to depict, but you're going to have a net bond dipole that sort of goes, I'll draw it in a different color to not confuse things too much any more than they already are. So I'll draw this in red. You have a net dipole that sort of goes between the two fluorine atoms in that direction. All right, so there's a net pull of electron density in that direction because these chlorines are not pulling back as hard as the fluorines are. So it really requires you to think in 3 dimensions to really think about these shapes. But as we'll start to see some patterns that are associated with this, and I'll give you a summary on the last slide that'll certainly be helpful for thinking about most of the cases you'll deal with. So there's one more note I want to make, and it's about molecules that are AXN, which means they have no lone pairs. We've kind of already seen this, and this is one pattern you're definitely going to want to recognize that'll save you a lot of time. I guess this should be AXM using the notation that we use. Sorry. All right, so if you have an AXM molecule, which means all X's are the same, so you can't have 2 different outer atoms as we saw, but if all X's are the same, and there are no lone pairs on the central atom, these are always going to be nonpolar. All right, so in other words, for those 5 basic shapes that we learned, linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, octahedral, if all of those positions are occupied by the same atom with no lone pairs in there, all of the bond polarities will cancel each other out. No matter how big or small those individual bond polarities are, they will cancel out and you'll have a nonpolar molecule. So we saw this 2 slides ago for linear, trigonal, planar, tetrahedral. It applies also to the higher ones as well. So if we have AX5, for example, and let's assume that the outer atom is more electronegative, as it usually will be, each of these bond dipoles is going to cancel out. So on the equatorial part of the molecule, the triangle part here, as we saw for trigonal planar, those all cancel each other out. They're 2-dimensional vectors, so the x component of this vector cancels out the combined x components of these 2, and then these 2 are sort of equal and opposite in the y direction. So that part cancels out, and then the bond polarities that go above and below that plane are also then equal and opposite. You have one pointing up that's the same and opposite as the one pointing down, so those also will cancel each other out. And the same story applies for AX6, octahedral. So for all of these simple geometries where you have the same outer atom and no lone pairs, it's going to be nonpolar, and you don't even have to really think about it any deeper than that for this course. But so that's one pattern we're going to want to be able to recognize. All right, so let's do a couple examples of this just to see how this works. And mostly what you're going to be doing, I'm going to give you a little bit more details in the notes, just to help you understand this a little bit at a deeper level. As you'll see when you do the homework problems and the exam problems, what we're going to mostly be asking you to do is, okay, here's a list of molecules. Which ones are polar, which ones are not polar? You don't really have to dive into the details of which direction the dipole is, or whether it's towards one side of the molecule or the other. Those kind of details are a little bit beyond what we're going to ask you to do, and they're hard to format into a Blackboard question anyway. But we are going to make sure you're able to identify which molecules are and are not polar. So for CLF3, we're going to predict the direction of the molecular dipole if present. So the first thing to do is identify whether it is polar, and then we can talk about whether, what direction that polarity is just a little bit of additional detail. So we have to start with the Lewis structure because polarity is also related then to the 3-dimensional shape. So we're going to count electrons. Each of these is in group 7. And so we're going to have 28 valence electrons in this molecule. Okay? And so when we arrange those around the central atom, we put our 3 fluorines. We complete the octet of the outer atoms first. Alright, so 3 times 8 is 24. We've used 24 out of our 28 valence electrons, which means we have 4 more to go on the central atom. So we have 2 lone pairs then that go on the central atom. Alright, so this is another 5 electron group structure where we have AX3, E2. Okay, so we have 3 fluorines, 3 X's, 2 lone pairs, E2. AX3, E2. The steric number is 5, if you want to think about it in those terms. And so that means we have 5 electron groups arranged in a trigonal bipyramidal fashion, and we just need to figure out where the lone pairs go. Now, AX3E2 is another one that people often mess up when they're doing these. It's very tempting to put the 2 lone pairs on top and on bottom and put them as far away from each other as possible, but we add the lone pairs sequentially. So the first lone pair goes on the trigonal planar part of the molecule, the triangular part, and the second lone pair then will also go there. So when you're adding lone pairs to the trigonal bipyramidal electron group arrangement, remember that they're all going to go on the triangular part, whether there's 1, 2, or 3 lone pairs. Okay, so those 2 go out there. The fluorines occupy the remaining positions. So we call this a T-shaped geometry, although that's not really asked here. And then we want to know if this is polar or not. So if we look at the T-shaped geometry, we have these 2 dipoles, assuming a perfect T-shaped geometry, are going to cancel each other out. So this bond dipole points straight up, this one points straight down. So those cancel each other out, but we still have then this one that goes left to right. So we're going to have a net molecular dipole from left to right, and this will be then a polar molecule. And again, we probably wouldn't ask you about the direction of the dipole, but that's the direction it's going to go. It turns out there's a little bit of a distortion here because of the lone pairs. So these 2 dipoles don't perfectly cancel each other out because they are bent back a little bit. But at the same token, they're pretty much pointing straight up and down. So those 2 cancel each other out, and the only net dipole then is going to be in the left to right direction to a good approximation. Okay? So that's how we predict the dipole of that one. We can do one more example together, and then I'll turn you loose with one on your own in a second. So predict the direction of the molecular dipole in CClF3. So this one here, we have to determine the Lewis structure for this. So we have carbon, chlorine, and fluorine now we have to count electrons for. Carbon is group 4, so it has 4 valence electrons. Alright, so Lewis structures aren't going to go away anytime soon, at least for this chapter. So we have to make sure we know how to do this. We have 7 valence electrons from chlorine, and we have 3 times 7 for the fluorines, 21 more. So in total we have 32 valence electrons for this compound. 4 plus 7 plus 21. We arrange the least electronegative atom in the center, which is going to be carbon. We put single bonds to the outer atoms. And we get this arrangement. We have 4 outer atoms, 8 electrons each. That's all 32 of our electrons. We have no more electrons for the central atom as lone pairs. Another pattern we'll see when we do Lewis structures, carbon almost never has lone pairs. The only exception I can think of is carbon monoxide. But really, in almost every case, carbon is not going to have lone pairs. It can have multiple bonds, double bonds, triple bonds, but it can't have lone pairs. So that's going to be the final Lewis structure, which is going to be tetrahedral. And it's very tempting to say, oh, it's AX4, so it's nonpolar. But remember, that only applies if all of the X's are the same. Here we have 2 different X's, chlorine and fluorine. So very similar to the example I showed you before, we have dipoles that don't cancel each other out. So if we draw this in 3 dimensions, we can put these in any arrangement we want. There's no difference in how we do that. Let's put the chlorine up top. So we have bond dipoles going in all directions here that point towards the outer atoms. But again, because the CCl bond is less polar, chlorine is less electronegative, this is going to be a smaller dipole. So this dipole that's pointing up towards the chlorine is not going to completely cancel out the dipoles involving the carbon-fluorine bonds. So in that, you're going to have a dipole moment that points down. So this is going to be also polar. And if we care about the direction of the dipole, it's going to point down towards the fluorines. Okay, because that pole is going to be stronger than, and it's not going to cancel out completely with the pole from the chlorine. Okay? All right, so those are examples of molecular polarity. Let's do one more clicker question that won't count towards your grade, just for fun, just to see how if you guys pick this up. Try to incorporate these more and more as we go forward, because it's more interesting than me talking the whole time. So, or hope it is anyway. All right, so then if you just want to practice, go ahead and work through this with your neighbor, and I'll start the timer again for this. So I'll just give you 2 minutes to do this one. It might not be enough time, but just to at least get you started before I go through it myself, because we are running a little bit low on time today. But feel free to work together. All right, so we're just about out of time. It may not have been enough time for all of you. That's okay. Just to see how those of you that responded did. All right, so 60% had B, and that is the correct answer. So you guys did way better than I expected on that. Good job. Okay, so let's go back and quickly go over that. So we're trying to identify the nonpolar molecules. And this is a very typical homework and exam question that you'll see. We'll give you a list of molecules and you'll ask. So I'm not going to go through all the details on this, but for SO2, what we should get is, when we draw the Lewis structure, and again, double bonds don't really matter for VSEPR, we get AX2E, which is a bent geometry. So in this case, we have sort of this geometry here, and the bond dipoles don't cancel out. So this one's going to be polar. For number 2, which is SF6, we saw that that one is going to be AX6. That's octahedral. And this one's going to be nonpolar, so that's one of our choices that's nonpolar. You have an AX6 molecule, no lone pairs. PCl3, we did this in class when we introduced Lewis structures, and I think also last time. So this is AX3E, trigonopyramidal. So it comes from the tetrahedral arrangement, but because we don't have a fourth atom up there, the bond dipoles sort of have a net pole pointing down. This is going to be polar. And then finally, PCl5 is going to be an AX5. And as we saw for all these AXN geometries, they're going to be nonpolar. All right, so if any of those tripped you up, look through them, but B is the correct answer. So the last thing I want to mention with just a few more minutes, just a minute or two, is we're not going to talk in great detail about this now because a lot of these topics are going to come up later on in the course. But molecular polarity is very important for things that you'll see later on in Chem 1, also for a lot of chemistry 2. You'll deal with things related to polarity, and if you take organic chemistry, it's a very big topic that comes up. So some things that depend on the polarity and why it's important. So we have certain physical properties. So things like boiling point, melting point, and so on. So those are going to be determined by the molecular polarity. We'll learn a lot about that later on in the course. Solubility, we might start to talk about solutions later on, things that are dissolved in other things. And you have sort of this mantra that like dissolves like. So if you're trying to predict whether one substance will dissolve in another, you often have to look at the polarity. So polar molecules dissolve in polar substances and in polar solvents and vice versa. All right, so when we start talking about solutions later in the course, we'll see that things that are polar tend to dissolve things that are polar, and things that are nonpolar tend to dissolve things that are nonpolar. And this also is an opportune time to tell one of my top 5 favorite chemistry jokes. So if you have a white bear and a brown bear, and they jump into the water at the same time, which one dissolves first? The white one, because it's polar. Okay, so I love that one. All right, and then the last thing, this is going to be something we're not going to really talk about in general chemistry, but the way that molecules react is often determined by their polarity. There are some features that are related to that. And so if you take organic chemistry in your future life, organic chemistry in the future, you'll learn all about how the polarity of molecules influences their reactivity, and that's one of the main themes in organic chemistry. So the last thing, which I'm not going to write anything on, but here's a table to help you out. So it's the AXE table that I had at the beginning, and now I've classified them all as either polar or nonpolar. Now, I don't encourage you to memorize this, but try to understand it. And keep in mind, though, that this only works for cases where all the X's are the same. If you have 2 different X outer atoms, it breaks down. But for a lot of cases, you can use this to help you predict. All right, well, I'll see you on Friday when we start talking about bonding.